Hello, friends. Welcome to Global Hack Week Machine Learning Track, Episode 3. We are getting up there. Fancy Appleby, good to see you. Polar Void. Is this Taukirk? Tell me if I'm pronouncing that incorrectly. Dead Nuggy, welcome. Polar Void. One day Will is going to play us something else and throw us off. Yeah, what if... No, I actually thought about offering that as like the prize for somebody winning a competition is like you get to pick one song that I'll learn how to play. The problem is, and I think we've talked about this before, is not every song is playable on the kalimba because it doesn't have, it only has whole steps in sort of your basic, your basic Dorian? No, your basic Ionic mode. I never learned the modes. Bird's kalimba version. That could be good. That could be a good time. Adam is at the beach. Thank you for tuning in from the beach, Adam. That's a lot of dedication. Check Discord DMs. 10 out of 10 recommended. All right, I'll bite. I'll check my DMs. Adam said, "Is water wet?" Holy cow. Okay, I'm going to show, if this is what I think it is, which is just literally the coast. I'm going to show it really quick. Let's see. Oh, where is OBS? What? Punch in. Nope, not that. That's not what I wanted at all. This is actually a little bit confusing to me. Y'all, every time I unplug my computer, there we go. Every time I unplug my computer, OBS like redecides what all the monitors are, and it messes it up, and I don't like it. This is the image that Adam sent, which is apparently the ocean just smashing and crashing water everywhere. So yeah, the question is water wet? I will say I'm a bit of a traditionalist here, and I think yes, water is wet. I know people make this case that wetness is the interface between the water and the non-water, and so you really get you get closer, like more wetness and more wetness and more wetness, and then once you are 100% water, wetness drops to zero. And to me, that's just a rather inelegant definition, right? It has you drawing this line that is a straight line for most of the spectrum, and then it says, but when you hit this one point, you have to drop down to zero. And to me, that just seems like if you have the ability to come up with a definition of wetness that is easily defined by a single linear curve, I would take that, right? So I would say that yes, like more water is more wet, and so 100% water is 100% wet. And that's where I land. But yeah, I know people have strong feelings about that. Adam is searching for Blahaj. Yeah, Adam, let us know. I don't suppose you really have any sharks up there near the Isle of Man, right? I imagine it's too cold for them, but I don't know. Maybe some orcas. Is anything really ever touching? Yes, it is. In any notion of the word touch that we take to mean anything, it has to. But yeah, of course not. Of course, you always got that little space in between. Let's see. It's like a slope line. If y equals 4, for example, the slope is infinity, not 0. Sure. Right. I guess my issue is more with the fact that you're defining. If you say that 100% water is not wet, you're defining like a piecewise function, right? You're saying over this domain, it's linear and more water is more wet, and then at 100% water, you're defining it as kind of a separate thing, which is fine. People, like there are real things in the world that have undefined points. The Isle of Man is wet. It's good stuff. Well, we are going to get going today. So where we left last, actually, drop in the chat if you're drinking anything. This is my favorite question to ask, apparently. I made myself another latte. It's decaf, don't worry. I'm taking care of myself. But it's all wet and cold in Seattle these days. It's wet in Seattle. It's wet and cold in Seattle these days, and I just like feeling cozy. and cuddling up with a cup of something hot is a really fun time. Pour one out for Fancy Applebee's monitor because it is apparently broken. Asgetta Spy is drinking lime soda, which I'm a fan of. Very tasty. So yeah, we are going to get into it. I think where we left off last time is we had played around with sort of our basic tools of if we had to build this from scratch, what would we do? And we got to kind of a not super comfy place, right? We realized like actually distinguishing, like figuring out when a sentiment is ironic or not is kind of hard. Even with our bigger data set, we didn't learn that much from our TF-IDF setup. But I would like to take the first, we won't spend that long, maybe 10 or 20 minutes, and really try to bring home this first thing we were working on and actually make a model off of it. And I'll use that as kind of an excuse to set up some conversation about machine learning. If you've attended these before, you'll probably know everything that I'm going to say. But if you are new to Global Hack Week machine learning, it's like nice to kind of run through the basics of what is machine learning. And when we say machine learning has happened, what does that mean? Also, if you excuse me for 1 second, I'm going to turn down the heat because I hear the heater going over here and it's annoying me. I don't know, can you hear the heater? Wait in a second, I'll turn it off and you can tell me if you hear it. Oh yeah, remember to check in. Thanks for the reminder. Here, let me drop the link. That's part 2. Where's part 3? I'm sure someone else is going to get to it before me. Boom. Remember to check in, everyone. You're here. You deserve credit. Can you make a mean Google Assistant? Oh, I like this as an idea. Maybe this is a future Global Hack Week. Firewater Ace asked, where can I find the code from track 2? And I will actually just drop that in the chat. So we're going to be starting from, let's see. Yeah, anyone with link can view. So this is the code from yesterday. And we're going to be starting from that to build our final model, or our final model from what we did yesterday. And then we're going to dive into TensorFlow and Keras and really bring out the big tools and try to get some better performance. But we're going to start by building our sort of dumb model just so we have a baseline that we can improve from. Yeah, absolutely. Stay safe, Adam. Don't get too wet, because if you get too wet, you die. I suppose it's mostly if the inside of your lungs gets wet, but let's just not have that happen. Okay, so let's dive back into it. Let me know in the comments if you want me to review the code from yesterday. Our sort of big idea was TF-IDF, which is, I think it's a delightful idea, but I know it can get kind of complicated. And what if we made this a little bit bigger? Let me know if that's visible or if you want it to be even bigger. So the really short version of what we did yesterday, we had a data set, or really had 2 data sets. I'll make it even bigger. Thanks for letting me know. That's probably as big as I can go, but let me know if this works. And so we have our data set of sarcastic and not sarcastic headlines. And we built a function to produce TF-IDF scores. So remember, we're looking for words that are associated with sarcasm and words that are associated with not being sarcastic, right? Which might be kind of just a hard task to begin with. And I think that's really why we're running into trouble, is that just the presence or absence of a word doesn't let you know if you're being sarcastic or not. It's subtler than that. But we started with, okay, well, what are the most common words in our sarcastic samples? And they turned out to just be words that are common everywhere, right? Words like I, or the word a, or the word the. They're just words that you find everywhere. So they're not very helpful. And so we came up with this metric of term frequency inverse document frequency, which basically means we're looking for words that occur a lot in a specific group, but are not that common in general, right? We want to select just for the words that are actually kind of rare, but are common within our individual samples. Glad to hear the size is good. Do we figure out why we had not super useful results yesterday? Yeah, so I think that the thing that I'll land on is that trying to identify sarcasm just from individual words. One is tricky. That's just a difficult. I don't think that you can get that far based on individual words. The other thing is when we looked at our big data set, which we can come back down, and I'll remind you that our data set is coming from we're really using a proxy data set where we don't have 1,000 samples of sarcasm and non-sarcasm, but what we do have is headlines from theonion.com and headlines from huffingtonpost.com. And the idea is that The Onion is a satire site. And so in general, their headlines are satirical, which is a kind of deployment of irony. And so that's kind of what we're getting at. But our original data set isn't just a pure, we collected 1,000 examples of irony and 1,000 examples of non-irony, right? And so one of the things we saw, which actually I'd like to do this, is just read more of The Onion. But so obviously we have more profanity in the Onion articles. So rarely is the word fucking in a Huffington Post article headline. But it appears in Onion headlines all the time. So we're picking up on something else, right? I mean, it's possible that sarcastic sentences are more likely to have profanity in them, but that doesn't make you sarcastic, right? Just using a swear word is not enough to say that's sarcasm. Yeah. That's apparently that was my my one swear pass, which I mean, I can just print more if I want to, but yeah, we'll say I used it. Not really intentionally, but it did come up. But the other thing I want to dive into is the difference just in the maybe what we would call the non-sarcasm related diction. So if we go back to theonion.com, I just want to go through a couple of these. Actually, okay, I want to see what they have under the local tab. So we have mother informs children that grandpa has died for real this time. Time's tough for local man who actually is superior to women. Adding insult to injury, man mauled to death by dog wearing puffy vest. I'm looking for one of the ones that it's like area man does X, Y, or Z. Okay, here I'm just going to search The Onion area man. Okay, we've got plenty. Area man too weak to carry dust covered Bowflex out to curb. And so it uses this language of like area man, area woman, area teen, or whatever a lot. And so it does make sense that this kind of pops up in our data set assigned to The Onion more so than it does in Huffington Post, right? So it's going to pick up all of the words that are really what we're predicting here is, did this article come from The Onion or from Huffington Post? Not is it sarcasm. And that I think is a lot of where our other, it's like these are useful signals. They just might be signals that are useful for not exactly what we want. Location neutral Florida man. Yeah, exactly. Yeah, Florida man. If you're not familiar with the joys of Florida man, you can just Google Florida man. But there's some crazy things going on down in Florida. Almost as crazy as the things going on over in the Isle of Man. Okay, awesome. So how do we actually turn this into a model? So I kind of alluded to this last time, but in machine learning, our basic idea of a model is something that takes in data and performs some kind of task. And in supervised learning, which is what we're doing, is it takes in labeled data. So data that we know, basically phrases that we know are sarcastic or not sarcastic. It does some kind of learning, and then it's able to predict things on the other side. So you showed a bunch of examples of sarcastic and not sarcastic phrases. And then you show it something that's not labeled and you ask it to predict, is this sarcastic or not, right? And so this is kind of our basic structure for what a machine learning model is. And so what I want us to do is to basically use this learning that we have. We have, maybe they're not the best words, but they are words we identified that are associated with these sarcastic headlines and these not sarcastic headlines. And so the sort of very simplest way we could do this, excuse me, I made cookies, y'all. They're the The peanut butter chocolate oatmeal cookies, they're very tasty. I need to remember that eating on stream just takes a lot of time because you have to like actually finish chewing and swallowing before you start talking again. So a very, very simple version of this basically is just counting how many words have high TF-IDF scores for sarcasm, and how many of the words have high TF-IDF scores for non-sarcasm, right? And so this is kind of going to be the basis of our predict function. So we'll define a predict function that accepts in a document, and this document is just going to be, just a string like our other headlines. And so the first thing that we're going to want to do is to pre-process it. And thankfully, we already have our pre-process script that if I type pre-process, does that autocomplete? We might actually have to rerun everything. Oh, yeah, it looks like, okay, we're going to have to rerun everything here. And people will comment, oh, hey, Will, don't you know there's like a run all button? And I know there is, but I like actually having a second where I actually think about all the things that I'm running. And it takes a second. Cool. There we go. Ironic terms freaks. We can just get rid of that. We're not using it anymore. Pre-process is not defined. Did we define pre-process later? We did. Okay. So let's run our pre-process. And now we can come back up here and run these. Awesome. So now we're going to download our real data again. We're sorting it out into sarcastic and not sarcastic. We're generating our TF-IDF dictionaries. And now we're getting the sorted tokens. And actually, printing it is nice, but we actually want to actually grab these in a list. So what if we actually say sarcastic identifiers, or we'll be precise and we'll say irony identifiers, and then down here for the not ironic, we'll call these non-irony identifiers. We've collected a list of words that tend to associate with sarcasm, and another list of words that tend to not associate with sarcasm. And we can just replace those. We just saved our two lists and introduced a. Where is our bug? Here we go. We just need to get rid of all of this. Okay, sweet. So we have our irony identifiers and our non-irony identifiers. And I just picked 20 as a random number, but if we were doing this for real, we could play around with this number and try to tune it to something that works better for us. This is kind of, if you tuned in last time, this is kind of when we were picking apart just based on the palette that different artists used. It's like, how large do we make the palette? How many different colors do we remember? So now that we have an irony identifiers list and a non-irony identifiers list, after we pre-process our doc, we can literally just count them up, right? So we can say, actually, you know, I want to be a little bit better than this. What if instead, well, no, yeah, actually, this is fine. Let's actually just up this number. Let's up this number to 100. So we have 100 words that are irony identifiers, and then 100 words that are non-irony identifiers. So we'll pre-process our doc, and we'll just say for word in doc, and we'll just count them up. And so we'll say count of irony identifiers, count of non-irony identifiers. And so for every word, we'll say if word in irony identifiers, then we're just going to add 1 to our count of irony identifiers. And then we can say elif word in non-irony identifiers. We can add 1 to our count of non-irony identifiers. So we're just counting up how many of these words are commonly associated with irony and how many of these words are not commonly associated with irony. And at the very end, we can make a determination, right? So the simplest thing we could say is, well, if the count of irony identifiers is greater than the count of non-irony identifiers, let's say it's ironic, and otherwise say it's not. But you could imagine trying to be a little bit more nuanced. Maybe we introduce a third category of like we're unsure. So we could even say if maybe we say irony delta. And so we could say irony delta is equal to our irony identifiers minus our non-irony identifiers. And so if you're not associated with either, you don't really count, and that's fine. And we can say if irony delta is greater than, let's say, well, let's start by just saying if it's greater than 0, then we can return, we'll return 1 as ironic. And then otherwise, we'll return 0 as not ironic. Yeah, the cookie is peanut butter and chocolate and oatmeal and a few other things to make it a cookie. But I would recommend that everybody go and make some cookies. It's cookie season, y'all. Fancy Applebee, what are you having for dinner? Polar Boy makes some good chocolate chip cookies. Yeah, Fancy Applebee knows what's up. Running all might cause you to run things that are broken or you don't mean to run. We should have a baking. I know in years past we have done Global Hack Week baking sessions, which is always a fun time. A Yoshi something bowl? I'm curious. What's a Yoshi something bowl? Ah, yes, we do have a stray colon there. Okay, so we have a predict function. So let's just test it out. Let's run it and see if we can just run it on a random bit of text. And what if we actually copy this one over? Area man too weak to carry dust covered Bowflex out to curb. See what happens. Boom! It predicts 1 as sarcasm, right? Okay. Now let's try to come up with a non-sarcastic headline. You can comment things that you think should be sarcastic headlines or non-sarcastic headlines. Okay. So here's a fun one. Are y'all familiar with this Liz Truss drama? I'm sure Adam is because he is over there in the shadow of Liz Truss's fallen government. But so Liz Truss was the UK prime minister that succeeded Boris Johnson, and there was this joke about a newspaper had a headline of like, "Oh, will Liz Truss's government outlive a head of lettuce?" And they actually set up a live stream that had on one side there was a head of lettuce out of the fridge, and on the other side there was a picture of Liz Truss. And there's a question of how long will she actually last in office? And it turns out she did not outlast the head of lettuce. The head of lettuce is still around, and Liz Truss is no longer the prime minister. And so there are real headlines that are like, Liz Truss did not outlive the head of lettuce. A head of lettuce. And so I'm kind of curious because this is one where it's like, it almost feels like a satirical headline, but it is true. Like they literally had a head of lettuce, and the head of lettuce lasted longer than Liz Truss's government. And this is interesting. It does say 0. It says, no, this is not sarcastic, which, I mean, honestly, I'm more impressed with than this is better than I expected. Yeah, sped run the prime ministership. Yeah, it is now, was it Rishi Sunak? Is that his name? To be clear, Adam, I said that you exist in the shadow of her government, and to be fair, you do, right? Yeah. So to be true, this like I am pleased that this model is getting this sentence correct, or it's getting this headline correct, as it's not satirical, but it's not like our model knows that, right? Really, it's that none of these individual words are sufficiently like raising the alarm of this might be satire. But it's not like it actually can go out and check, is this true, right? And this is kind of why we started with our Kahoot yesterday, where we actually checked, are we able to tell the difference between sarcasm? And we didn't do that great, right? We got better than 50%, but not that much better than 50%, because in so many of these cases, we just don't have the context that we need. So we've created a predict function, and now I want to actually test our accuracy. So the very simple thing that we could do to test our accuracy is get our original, remember our original data frame, we called it df. And so we have, oh wait, this is our original one. I think we called it real df. Not real minus df. Okay, awesome. So we have the headline, and then we have this is sarcastic. And so this is sarcastic is like the truth of, of is it sarcastic or not. And the headline is kind of our input text. And so to actually test our model now, we can actually call predict on every single headline and then see how often our prediction matches the truth, right? So one way we can do this is we can say real df dot apply. And apply is actually a really, really handy dandy method of data frames that lets you run a function on every single thing in a column. So what we can say is we can say real df headline dot apply predict. And we might need to add an axis. I want to just see if we can run this. Okay, it is actually taking a non-trivial amount of time. But so you can see it gives us a big old chunk of zeros and ones. And so what we could do is we can reassign this to a new column. So we could say real df prediction equals this this thing that we're spelling out here. So we're basically taking in the headline, running predict on every single headline we have, and then storing that in a new column called prediction. So now we can look at real df in sarcastic and prediction. And not read df, real df. So boom, here we go. So we have basically our predictions versus the truth. And we want to see what percentage of the time our prediction is matching the truth. It says I hate MLH is not ironic. Wait. Does it? Where was the this was in the non-real df? MLH is not helping. Wait. Is this later on? I love MLH. Where's I hate MLH? I don't see it. I do love some drama though. Let's see. Yeah, we're gonna check to see if it did better than us. We can also test it on the ones that we provided. We'll give that a shot as well. Actually, maybe it makes sense to do that one first, because that one's sort of like lower drama. Or actually, it's probably higher drama, but it's just less indicative of if what we did is like correct. Okay, so let's rebuild our. Actually, we should already have our irony identifiers. Okay, so these up here, these were our ironic and not ironic sets from our personal data set that we constructed. So let's say maybe not 5, maybe we'll say 20. And we'll call this our data set irony identifiers and R data set non-irony identifiers. And let's run this again. Whoa. And in fact, this is good. We can generalize our function down here. So this predict function that we ran, we can actually update it to say you can pass in your own list of ironic and non-ironic identifiers. So we can say irony identifiers, non-irony identifiers. And by default, we'll just set those equal to the global irony identifiers and non-irony identifiers. So this is just a way that we can basically pass a sort of default parameter here. So by saying, oh, by default, irony identifiers will be our list called irony identifiers, and oh, not iron identifiers, non-irony identifiers. And so now it'll use those defaults unless we override them. So we're going to run this again. And so now we can test this on our personal data set. So remember, our personal data set just has ironic as a 1 or a 0 and then the text. And so what we can do here is we can define a function that just uses our personal, let's see, our data set irony identifiers. So we'll say our data set predict is equal to a lambda, where we just pass the text into our predict function with our data set irony identifiers and our data set non-irony identifiers. So this is a little bit of a complex line here. Ask me if this is weird for you. I can talk through it more. But basically, we're just creating a version of predict that uses our data set irony identifiers because the identifiers will be different from the different models, right? So we're training on our data set, and then we also want to test on our data set. And so what we can then do is for regular DF, which is our personal data set, we can do the same thing we did earlier, where we call apply on our text and pass it our personal data set predict. And this gives us our predictions. And that runs pretty fast. And so now we can just see what our predictions look like. And then we can actually calculate our accuracy. Oh, that's interesting. It looks like it's actually going to do pretty well. Show. Oh, right. Head just shows you the first. Let's look at all of them. So actually, it looks like we might. Okay, it looks like we're just way over favoring sarcasm. That we're predicting a lot of them are going to be sarcastic. So that we can just look kind of in the individual case. How often did we get it right? And it looks like we got a lot of our sarcasm ones right, but we got most of our non-sarcastic ones wrong. But we want like a better metric. We don't just want to say, yeah, I looked at it and we got most of them right or wrong, right? We want to actually come up with a summarizing number that tells us how good we did. And one of our basic numbers we look at in machine learning is accuracy, right? This is just like, what score did you get on the test? How many questions did you get right? And so the way that we can calculate this is we can basically just check the number of times our prediction equals the sort of ground truth. So we can say df ironic equals df prediction. And we can call this df correct. Does that work? I hope that works. Okay, awesome. So now df correct basically has true in it if we got it right, and it says false in it if we got it wrong. And so now what we can simply do is just ask for the average. So I think we can just say .mean on this. Boom. Okay. So we got, this is actually super interesting. We got 54%, which I think is actually a really cool result to get, which is slightly better than random guessing, right? Maybe not that much better than random guessing, but certainly better. We could also try a small data set with the words in the large one. Yeah, we could mix and match, and maybe that's an interesting thing to compare. Actually, I'm interested in it. So we came up with our list of important words from our data set, and we did slightly better than random guessing. What happens if we do the same sort of predictions, but we use the words we learned from the really big data set? So this, we should be able to do a pretty similar thing where we can define, we'll call it predictions from the big data set. You know I'm into these long variable names. And so we'll say df headlines, or no, this is just df text, isn't it? And we'll say dot apply predict without any special bindings. We're just predicting based on our default one we built from the big data set. And so this should give us our new predictions. And now we can do this same math of how often did our prediction get it right. But instead of predictions, we'll say predictions from the big data set. And we'll call this correct from the big data set. And now we can do the same calculation and just say, on average, what percentage of the time did we get it right with dot mean? And this says exactly 50%. And I think this is interesting. And I'll admit, this is probably what I would have guessed something close to this. Maybe not this exactly. But the idea is that, yeah, actually, trying to go from one kind of realm of sarcasm to another doesn't always work. And I think this is actually maybe something we can think about, like in sort of the human world. That I'll say that when I am with people that I'm really close to, that I know pretty well, I can 100% tell if they're being ironic or if they're being sarcastic. But when I'm with strangers, or like, I don't know if you've ever noticed this, if you're with people in a different age group, like if I hang out with my, like the friends of my littlest siblings, or like the friends of my parents, they're going to like make ironic jokes that are just going to go right over my head, right? But if I'm with people that I talk to a lot, I'm going to be able to figure out if they're being sarcastic, with a higher degree of accuracy. And that's kind of what we see here, right? Again, the difference isn't even that bad. It isn't even that big. It's, we did 4% worse, right? We went from 54% correct to 50% correct. I agree. It is very satisfying that it landed on exactly 50%. But so we're out here, we're experimenting, and we're gathering some performance data, right? We're seeing how accurate is our model. And so now I want to go to sort of the final thing before we pull out the big guns and we try to use not Terraform. We use TensorFlow. The tangent. I actually haven't gone on that many tangents today. The tangent is that in my work at Google, I use a piece of software called Terraform a lot that lets you like manage the state of the cloud, kind of. But TensorFlow and Keras. Before we pull those out, the last thing I want to do is actually get a prediction based on this model and our big training data set. So fancy app will be, yes, we're going to test the big data set as well, which actually we kind of already made our predictions. So down here we have is sarcastic and our prediction, and this is for the big real data set. And so we can do just the same thing here, where we say, I'm really editing this line out of order, but hopefully it makes sense. So we'll say real df correct equal to if our is sarcasm value is equal to our prediction value. And so then all we have to do to get our accuracy, moment of truth, can I get a drum roll, please? I don't know how you would drum roll, but I'm going to tell myself that somebody out there is drum rolling on their desk. Oh, that's not how you run a code. Okay, interesting. 69.97%. So much better, right? I would say actually much, much better. This is, I would say this is rivaling sort of the average human ability to tell if someone's being sarcastic, even with context. And I mean, in some ways, our task here is actually easier because As we talked about, Onion articles have a lot of other identifiers besides just is it satirical, right? They're satirical, but in a particular way. And so, sure, maybe it's a little bit of an easier task, but we're getting 70% accuracy. Nancy Appleby, thank you for rumbling. Dead Nuggy plays the drums. Oh, we'll have to patch you in from like an what is it, like the guest invitation link, so you can do a drum roll for us. So yeah, I like this because I don't think that it is anything to sneeze at. I think this is like, if you're just trying to distinguish between two different kinds of text and you have a lot of them, doing a basic TF IDF check to see, do you have more words that are important for this group or the other, is not terrible. And importantly, this was pretty easy to code, and it was actually really easy to run. I know on the first day we had some questions about, do I need better hardware to like do serious machine learning? And I think there's a lot of answers to that question. We ran through a few. We provided a lot of different answers to that question. But one of the big ones is there are so many different powerful things you can do without using that many compute resources. And so oftentimes it's a good idea to try the easy things first and only try the hard things if you know you need to do them. Fancy Appleby plays the violin. We could totally put together a Global Hack Week band. Global Hack Week Orchestra? I don't know. Let me know if you're interested. Okay, awesome. So we are, I think, in a good place. We messed around and we tried to build our own model, and it did okay. I think especially when we had more data, it did actually quite well. Probably better than we have any right to expect it to. So now what I want to do, and maybe we'll do it in this same, should we start a new workbook? Let's start a new workbook, actually. So come up here and just say new notebook. We'll call this one Global Hack Week 2022-10, part 3. Excuse me. Okay, so the first thing that we want to do, share my new one? My new what? I guess we're basically halfway. I don't need to go to the bathroom. Sometimes I'm like, this is the time for me to run to the bathroom to take a break. I'll just have some water instead. Oh yes, the new workbook. Yeah, I mean, there's nothing in it right now, but I will go ahead and drop it in the chat. Boom. Anyone with the link? Total anarchy. Okay, so here we go. We are ready to get serious. So for folks that have not been in this rodeo before, we like to kind of try to build things from scratch, but there are so many powerful tools out there that help you build more sort of complex, more powerful models really quickly. And one of the big ones is called TensorFlow. Now, TensorFlow itself is really powerful, and it also in some ways is, I don't want to say overcomplicated, but it gives you a lot of control. And sometimes it gives you control that you don't even necessarily want, right? And so that is why we are lucky that there is this wrapper around TensorFlow called Keras. And the way that I would think about Keras is that it's almost like Legos for machine learning, is it gives you a bunch of these individual parts that you can kind of put together like Legos to build your model. And so that's kind of what I want to start diving into now. And I'm not sure we'll get to the end of it, but I at least want us to try to get to the point where we have a basic model in Keras running. And we're going to try to predict with this new model. Keras equals I could care less. No, Keras is great. Keras is awesome. I'm a big Keras fan. Keras cares about us, and us cares about Keras. That's what I'm going to say. Boom. Okay, so we're going to copy back over this command because it has our real data set as well. That should take a second to run. And we will again import pandas as PD. and we'll get our training data set as pd.read.csv. And we can go and grab that path again for our training data set. Copy path. I'm actually kind of curious. I've been deleting this content. I imagine it'll error out, but I wonder if it'll just work. It just works. Okay, so I guess the content starting slash or the starting directory is just kind of an alias of some sort. So you don't actually have to delete that, which is good to know. Okay, so now I'm always torn on whether or not we just import everything all at once, or I just tell you, oh, this is what we're using this for. Let's import it. And I think that we're gonna import a chunk of things that we will use over the rest of this stream. So we're going to import NumPy as NP. NumPy is a really useful, I think we may have used it, well, we've definitely used it in past Global Hack Weeks, but it is a really useful library with a bunch of math functionality, functionality for interacting with numbers. The main thing it gives you is really nice matrix operations. So if you have never taken a matrix algebra course, matrix math is sort of arbitrary number of rows and columns. So it's kind of like a nested list or a two-dimensional list, but we end up using it, or really an n-dimensional list. But we end up using it a lot in machine learning. We already imported pandas. We're going to import matplotlib.pyplot as PLT. We'll use this for visualizing how our model is doing. We, of course, have to import TensorFlow. Also, I don't know if I explicitly told you all this, but the as basically lets you give an alias to the thing you're importing. So basically, I'm saying import NumPy and let me refer to NumPy as NP. And import matplotlib, but let me refer to it as PLT. And for TensorFlow, it's really common to say import TensorFlow as TF. We can let's import Seaborn. Seaborn basically gives us nicer graphics for matplotlib, which is nice. We'll also want to import NLTK. We'll use some of that stuff again. I think we're going to use some regular expressions as well. And then let's also import stop words. So from NLTK corpus, import stop words. We briefly talked about this yesterday. So one way of filtering out unimportant things is you can use TF-IDF. And there's another way of doing this where you just have a list of those really, really common words that nobody cares about. And those are called stop words. So words like a or am or I are all just short enough that we basically say they're probably not containing that much information, and we can filter those out. Yeah, we can import TQDM. Okay, this is an interesting question. In normal coding, do you use Copilot or Tab9? I'm not familiar with Tab9. I am familiar with Copilot, and these are like tools that kind of help you autocomplete code and stuff. And this is y'all getting me on these tangents, but they're always fun. So the answer I give is generally speaking no. I mean, the main reason is that when I'm coding for work, I use this. It's like a Google internal IDE. So it's this kind of special Google way to code it's called Cider. But that is like a sort of proprietary IDE, and they actually do have a version of this inside there that does do some of this auto-completing stuff. And the reason that I do use it on occasion, like our special internal Copilot thing. And it is like interesting and spooky how good. I mean, it's basically it can do like autocomplete for coding. And sometimes, I mean, these things are getting really, really good. And sometimes it is spooky, like how much it understands about what I'm about to do, right? Like the pattern it's able to pick up on. Some of the patterns are obvious, and you're like, oh yes, like function definition. If I start typing DEF, or if I start typing DE, like probably the next letter is F. Like that's not a big deal. But like even complex things where it'll automatically generate like nested if statements for you and stuff. And I do use it occasionally. Usually it ends up not being that helpful. And the reason is because the ratio in my actual work of like thinking to coding that I do is way different, right? I come here for Global Hack Week, and we're like actually writing quite a bit of code relatively quickly. At work, I will, I will like go and think about something for several hours, and then I might come in and like write 3 lines of code, right? And at that point, it's like, well, if I'm thinking a lot about it, and then I come in and write 3 lines of code, it's like I don't need to write those 3 lines of code faster, right? It's going to take me like 2 minutes to write them anyway. If I was coming and chunking out, a really, really big piece of work, then writing, large pieces of code faster would be useful and important for me. So that kind of, I guess, gets to the what kind of programming are you doing and how much code do you write versus how much are you just kind of thinking about it. But yeah, Copilot and the and other sort of autocomplete functionality for programmers, they are getting crazy good, and I'm a big fan. I think they're really neat. Good stuff. Yeah, let's import TQDM. From TQDM, import TQDM. It's a really nice way to show you progress when you're running big loops. And then we're just going to import a few Keras functionality. So remember, TensorFlow is sort of the underlying technology that gives you a lot of power, but can be kind of tricky to deal with. And Keras kind of gives you this nice wrapper around it that kind of turns TensorFlow into Legos. So we could say from keras.preprocessing.text, import tokenizer. So remember, earlier we were using the word tokenizer out of NLTK, but the Keras tokenizer is also really, really powerful. We'll also say from TensorFlow.keras.preprocessing.sequence, import pad sequences. We'll get into this a little bit more, but the kind of model we're going to be building will actually look at the sentence sort of in order. Earlier, we were just counting up individual words. And so we often refer to those kinds of models as bag of word approaches, where you don't really care about the order. You're just kind of looking at you throw all the words into a bag and you kind of count them up. Whereas with this model we're building, the order actually will be important. And I think that we'll talk about this a little bit, that sarcasm and irony is something that, like the subtle relationships between words actually kind of matters. And so because we're creating them in a sequence, padding those sequences so they're actually the similar lengths is really helpful. And so what you end up doing is you end up adding basically a bunch of zeros at the end to make all of your sentences roughly the same length. Finally, we can import from Keras models. We can import the sequential model. This just basically says we're going to stick all of our Legos on top of one another and create a sequence of different layers for our model to function with. I also want to suppress some warnings just because they're annoying. So we'll say import warnings and say warning.filter warnings. And we're just going to ignore some warnings. And TensorFlow.keras.preprocessing.sequence. That looks correct. Okay, let's see if we can import everything. Uh-oh. Maybe we just try importing it directly from Keras. Let's give that a shot. You can do we have to manually install it? That'd be a bummer if we had to manually install it. Oh, it's not because we imported TensorFlow as TF, is it? No. But we did. It says no module named TF. Okay, let's see. We might have to check out Google and have it tell us what's going on. No module named Keras preprocess. In fact, let's even say Google Colab. Let's see. This is where the magic happens, is me getting an error message and just throwing it in there. See, TensorFlow.keras.preprocessing.sequence. Is that not what I originally had? Keras. Oh, preprocess. Oh my goodness. Okay, and we might have to do TensorFlow at the beginning as well, or will that just work? Let's try TensorFlow at the beginning. Incredible. Okay, so we would have gotten there eventually, but Fancy Appleby, thank you for the help. Right on. Oh, okay. I don't know if y'all can hear it, but it is raining kind of heavily outside, and I love it. This is one of the biggest things that I actually miss coming to Seattle. Is in Seattle, the rain is always so soft, and it's something that it's like you come to Seattle and you hear it rains a lot, but it never really actually pours. So whenever it actually rains and you can hear it raining, I'm always super thrilled. Okay, so we've done our big import chunk. And now let's take another look at our data set. So we have our training data set. This should look familiar because it's the same data we've been working with. Oh my goodness, Samrid, welcome, welcome. It's good to see you. But yes, Samrid, if you because you've attended these before, you should be able to jump in. Here, I can share my link again. Seattle, if you don't know that much about Seattle, usually the two things that you know is that there's a lot of rain and there's a lot of coffee. You may also know that Amazon is based here. Microsoft is also based here. What else do people usually know? There are mountains here. The mountains are great. Those are like the big, I don't know. I feel like those are the Seattle brand things. Okay, right on. So we have our training data set. This should look really familiar. We just used it a few minutes ago. Something that we didn't do before, because now we're kind of entering adult mode, and it's like, okay, well, what do we do, when we're trying to be professional machine learning practitioners? So one thing we can do is just check to see if we have any null values. So we can say train is null, and then we can just sum up the null value, like how many nulls there are. And luckily, there are no null values. So this is a relatively clean data set for us, which is great. We don't have to filter anything out. We can also just describe our data set. So we can say train.describe. And this gives us a little summary. Oh, right. And because by default, it ignores things that aren't numbers, we can say include object here. So this is a little bit of a nuanced thing, but Pandas, because it tries to optimize things, it places things in two categories. Either you are a data that is an object, or you are data that is not an object. And basically the only things that get to be not objects are numbers and Booleans. And basically everything else is an object. So strings, including, are considered objects. And so in a lot of cases, if it's trying to be really efficient, it will ignore the things that it says are objects. Oh, that's interesting. It filtered out that is sarcastic. I'm going to look at the documentation for this really quick because I want to see everything. So pandas describe. I feel like I should model more of this, of just like looking up the documentation in front of everybody, Okay, so the include parameter. Okay, so we can just say all instead of object. So we'll say describe include all. So that should give us both the objects and the non-objects. Great. Okay. So we have is sarcastic. So this basically tells us that 47% of our entries are sarcasm. The standard deviation doesn't really mean anything. Unnamed is kind of useless to us. But we can see that we have 22,895 headlines. We can also see that actually there are some repeats. So there are 12 headlines that are like the most common headline has 12 of it, and the most common article link has 2. Oh, which actually, okay, now I'm looking at this, and it's a little bit dark, but whenever there is a school shooting in the U.S., which is a thing that happens frequently enough that we have to say when it happens, The Onion posts this same headline, which is no way to prevent this, says only nation where this regularly happens. And so, so I believe they post the same headline every time there is a high profile mass shooting, which is just a real bummer of a thing. But I guess that's satire for you. So this is, I guess, for our purposes, besides, I suppose like trying to push policy that actually will reduce gun violence. We also want to probably filter this out because we don't want duplicates of it in our data set. So we can drop duplicates. We can check how many duplicates we have. We can say train headline dot duplicated. And we can just sum that up for how many duplicates we have. We have 91 total duplicates, so a lot of duplicates. I guess there's a lot of reposting the same headline, and so we can drop our duplicates. And the way we'll do this is we will say train dot drop, but then we want to actually get the duplicates. So the way that we can do that is we can say train. So we want to do train headline, and then call duplicated. So this will be true if it is a duplicate, and we can actually grab the indices of this. So we can say train all of the rows that are duplicated, and then get the indices of that. And we'll have to pass in axis equals 0. And then that was kind of a complex line there. But so we're basically getting all the individual rows that are duplicated, pulling them out, getting the indices of those rows that are duplicated, and then dropping them here. And so we'll want to actually replace our train df with this. Polar Void says even a few links. Ooh, I'm not 100%. Oh, on the duplicated links. Yes, that looks, yeah. We've kind of ignored the links, but now I'm kind of curious to see what that is. Nation not sure. Nation not sure how many ex-Trump staffers it can safely. Nation not sure how many ex-Trump staffers it can safely reabsorb. It was from December 21st, or so December 2021. Wild times. Good stuff. So we've gotten rid of our duplicates. Fancy Appleby said, I'm trying to use data spell and I'm mentally dying. What is data spell? Shouldn't we keep one is a great question. Let's actually look up pandas duplicated. Pandas duplicated. Only consider certain columns for identifying duplicates. Sure. And okay, yeah. So keep. So this is I think the interesting field here. And the default is first. So by default, it'll mark duplicates except for the first one. Yeah. So this should by default be keeping our first one. But it's a good question to ask. I think that was my memory, was that it did by default just keep the first. So the first is not marked as a duplicate. The subsequent ones are. Data spell is a Jupyter Notebook IDE, so I can take advantage of my RTX. Ah, I see. Yeah, it's super nice to have your own hardware that's actually useful. Can't relate, but I support that. Okay, so we have cleaned up a little bit of our data, and we have seen our percentage of sarcastic and not sarcastic. And now we're going to do a little bit of, we're going to rewrite some pre-processing steps. So let's download our stop words. In fact, actually, I'll give us a little title. Build up a pre-processing function. And one of the reasons that having a good pre-processing function is pretty important is because you want to be able to use the exact same thing on your training data and your testing data, right? Your model is going to be expecting the data to be in the exact same format. And so by building up a pre-processing function, it can help us ensure that we're not giving the model different data when we're testing it. And they should be in the same format. Polar Void says, next Global Hack Week, can we do something audio related? Yeah, I'm actually very tempted to do this because I don't know. For a while, we kind of just ran through different kinds of formats. We started with tabular data, and then we did natural language, and then we did visual. We did pictures, or we did art images last time. Now we're going for round 2 on natural language. The video and audio are two sort of spaces that we haven't touched yet. And video is just hard because it's such, even if you're making it a very granular, like 10 by 10 pixel video at like 1 frame a second, it's like still hard to actually just run all of that. It just requires a lot of compute to do ML on videos. But audio we could actually do. I'll admit it's the thing that I know the least about, so I would have to do some learning before I host that workshop. But it does sound fun. So I'll give you a chance to drop that in the forum as well. And yeah, I don't know. Let me know in the comments if you want to do some audio processing next time. Okay, so we're building our pre-processing function. I mentioned this before. Let's actually download our stop words. So we can say, just like we downloaded punct from NLTK, we can say NLTK download, and then just say stop words. And then we can actually, from our stop words, grab all the default English stop words. So we'll say stop words. We can say, let's create a set of stop words dot words, and we can pass in the English parameters, which just tells us, give us kind of the default English stop words. Stop words. Stop words. That's what we downloaded. NLTK has no download. Words. It's words plural. We're getting all the little typos today. Okay, so now we should be able to take a peek at what our stop words are. Okay, cool. So if you scroll, there's actually a lot of stop words. There are plenty, but they are all words that are deemed sort of common enough to not really contain that much useful information. And a lot of scholarship has gone into, well, what stop words should really be considered stop words. And sometimes you want to keep all of them in. But it's an interesting thing to play with is, well, what if we remove stop words? We can also get rid of punctuation. We noticed a lot of specific punctuation in the Huffington Post headlines. And so we could actually include punctuation. So we could say punctuation equals a list of punctuation. Is that how you spell punctuation? And we can actually just add this punctuation to our stop words. So we can say update with our punctuation. Oh, did I forget to import string? Where was that supposed to come from? Oh, right. We're going to import. We didn't import the string library. In fact, let's also import string and Unicode data. We might use that. Okay, so string just has some useful little utilities, including a list of punctuation. So now if we look at our stop words again, we should have, lots of punctuation sprinkled in there. I guess the main ones are down here, but okay, yeah, a lot of punctuation up top as well. Fun stuff. Okay, so let's keep going on our pre-processing functions. We got any questions? Everybody following along? Everything going well? Hopefully. So we can do a basic split our. Here's what I do. We can do a basic sort of splitting our text into words function. So let's say split into words. And we'll say doc, and we'll just return text.split. We're going to do a lot of function composition today. We can also, actually, I don't know if we need that many individual functions. Trying to decide how I want to do this. Yeah. Okay, let's write a remove punctuation function. So we'll accept this time we'll accept a list of words. And we'll create a regular expression. You don't have to understand that much about regular expressions. It basically is just a way of creating a pattern that you can search through in text. And the reason that we have like a special library for it is because it comes up so often that you want to be able to do it really, really efficiently. And so here, we're going to basically just try to get rid of any individual punctuation marks. So we'll say any groups uh, of our punctuation. So this basically creates our pattern for us, and then we can use it on each individual word and pull out any punctuation. So we'll call this stripped of punctuation, and we'll use a list comprehension. And so we'll say our punctuation regular expression dot sub, and we'll basically replace we'll replace every time we match a punctuation with nothing. And we'll pass in W, which is for W in words. So for every word, we're going to filter out any individual punctuation. Let's see. What is re.escape? Yeah, so what that does is this is a great question. So normally in regular expressions, if you I guess there are two levels here. So normally in regular expressions, just like if you want to match anything, you have to escape it if it is a kind of special character, right? So for example, if I just wanted to say let's see if I can just do a basic example here, rematch. And so I believe normally you pass in the the normal string you're working with. So I could say, hello, my name is Will, and the pattern you're trying to match. And so the easiest pattern is just like some characters, right? So like hello. And if I run this, nothing happens. Oh gosh, do I have to extract a match group? Groups, maybe? No, none type has no group. So apparently did not find it in there. Maybe this is reversed. Maybe I need the pattern first. I might have to pull up the documentation for regexes. Okay, great. So we have, yeah. So here you have your pattern you're looking for, and then later you have your string you're matching over, right? But okay, let's say that I'm looking for kind of a weirder pattern. Let's say my pattern actually has some quotes in it. So I'd say my name is Will with single quotes around it. And it's like, okay, so obviously I need backslashes in front of my quotes. But let's say that I actually want to match anything, like any text inside of quotes. And it's like, okay, so in here I would have to say, well, I'm looking for a quote, and another quote, and then some text inside here. And so text is usually, you can say backslash W with a plus just says match any number of sort of normal text, normal word characters. So if we run this, it did not match, which is unfortunate. And it might be because I don't want to get too deep here. Oh, right. Okay, so this is actually gets to the core of it. Is we do backslash W to say, oh, hey, I'm looking for any number of word characters, but the backslash actually gets kind of eaten up because you actually, in order to have a normal backslash, you need to do a double backslash, right? Because normally a backslash is used for escaping, and so if you want to escape a backslash, you have to do double backslash, which looks like that's not matching as well. But yes, you can create what's called a raw string, which is usually thought to be sort of like the quote unquote solution for adding ever number of increasing backslashes by just putting an R at the front. And so the R at the front basically says, this is a raw string and interpret backslashes just as normal backslashes. And I think the sort of usual way that people say this is useful is it just allows you to avoid including like 12,000 backslashes in your string. And so that's kind of the purpose of escape here. It's just adding the backslashes for us is sort of the simple way that I would explain it. I know there's a very, very long explanation for very, very long explanation for what regular expression dot escape is. Okay, cool. So we're removing the punctuation. We can just return that, return stripped punctuation. What else do we want to do? We want to remove our stop words. Let's say def remove stop words. And so we can say we already have our set of stop words, and we can say words. We can say kept words equal to an empty list. We can just say for word in words. Say if word is not in our list of stop words, then we'll add our word to our list of kept words. This is just a way of filtering out the stop words. Cool. And then actually at the very end here, we're going to actually rejoin this into a regular sentence again, so we can on the back end use our fancy Keras tokenizer. So we'll say def preprocess. We'll say our preprocess because Keras has its own one, and we'll accept some text. And so we'll say words is equal to text.split, and then we'll say the text.lowercase. Text.lower.split, and then we'll say words is equal to remove punctuation of words. So we'll get rid of the punctuation, and then we'll remove our stop words. So we'll say words equals remove stop words of our words. And then finally, we're just going to return this sort of turn back into a normal sentence where we will dot join our words around spaces. And this will give us a pretty, it won't read as quite as seamlessly, but it might actually be helpful for removing some of the noise in our text. So if we say our preprocess of we're going to have a great time. Run this. Oh, can only join an iterable. Interesting. Oh yeah, we didn't return our kept words. Return kept words. Kept words is not defined. Oh, kept words, not kept words. Kept is a weird word, honestly. Okay, sequence 0. Item expected stir found list. Oh yeah, we're appending words, not individual word. This is great. We're catching all our bugs. Okay, cool. Going great time. So it removed all the stop words, which turned out to be a lot. It removed punctuation, and it leaves us with just like a very clean, very simple thing. If you think about it enough, words just sound weird. Ain't that the truth? Yeah, my favorite one is the word quarter. Like, say the word quarter 7 times. Quarter, 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 quarter. What's even going on in my mouth right now? I don't know. It's not a real word. You can't change my mind. Great. So now we're going to use our preprocessed string on all of our text. So let's say train, and we'll say clean headline is equal to, we'll use that apply function we used earlier. So we'll say train headline dot apply, and we'll use our preprocess. Sweet. So now we will pull out our labels, and our labels in this scenario is sarcastic. And then our actual raw data is going to be our clean headlines. We're getting some labels and some data, and we're separating them out mostly just so we can feed them into our model separately, like we want to. And we have a separate test data set, but we actually want to split this out into our sort of own training and validation set. So we can say, let's say our train ratio is 80%. So we're going to train on 80% of this and then test on the other 20. We can say our train size is just going to be the length of our labels times our train ratio. But we'll turn this into an integer. We can say our actual data will just be the first portion of it. So we can say train, not data. Train data is equal to data. We haven't talked about slices this session, have we? So slicing is a really useful thing in Python. I'll do a really quick example of this. So if I have a list called my list, and I have 1, 2, 3, 4, 5. Actually, let's go with 10. And if I want to get the first 3 things in my list, I can do what's called a slice. And so what I do is I put a colon and then I say 3. What this gives for me is starting at the beginning and going up through index number 3. I can also do this in reverse, and I can say, okay, start at index 3 and go through the end. So this basically starts at index 3 inclusive and goes until the end. And you can, of course, cut it sort of in the middle. So you could say start at 3 and go through 6. And so you get, index number 3, index number 4, and index number 5, and stopping before you get to 6. So that's slicing. It's super useful. And we can use it here to basically say, give us the first 80% of the data in a really clean way. So we can say our training data basically says go and count through until our train size. And our labels will do the same thing. And then we can do basically the inverse to get some testing data. So we'll say test data equals data, or we'll call this valid. Yeah, we'll call this validation data. Which will be, instead of starting at the beginning and going through train size, we'll start at train size and go through the end. And we can say validation labels. And similarly, we'll start at however big our training set is and go through the end. There's a question. They're similar to ranges, right? And this is on slices. And yes, I mean, so ranges sort of generate generate an iterable, and slices can be used to, get a segment of that iterable. But I mean, they do have a similar, you have a start, a stop, and you can also have a step as well. So in that kind of framework, they use a similar paradigm as ranges for sure. Okay, awesome. We have our training data and validation data all batched up. And so now we can use our tokenizer. So this is, remember, the Keras tokenizer, which is, honestly, we could do a whole global hack week just on the Keras tokenizer. It is super neat and super powerful. But so one thing we're going to do here is introduce what's called an out of vocabulary token. And this is something that you may have come up against, or you may have asked yourself. I mean, so for starters, how many unique words do we have? I don't know if we actually counted this to begin with. If we go back to part 2, did we ever count how many unique words our big data set has? Like, I know we counted in TF-IDF. We grabbed the top ones. Let's see, if we go up here, we have our irony identifiers, and we grabbed the first 100, but we're just like, what is the list of this? Or what is the length of this? Okay, so 27,365. So this is functionally the size of our vocabulary. This is the number of words we saw in our training data set. And this is a lot of words, right? Like, don't get me wrong, 200 or 27,000 is like large. I know a lot of times people will say that if you know 10,000 words in a language, that's where you can start to sort of approximate fluency. Obviously, it's different for every language. But like, hey, I'm trying to learn Spanish right now. I would love to know 27,000 words in Spanish. But it's not all of the words, right? There are still words out there that are not going to be in our list of 27,000 that we have seen in our data set. And this is one of those questions that before I came across this, I was like, well, yeah, like how do you deal with if you get a new input that is not something you've seen before? And the answer is by using an out of vocabulary token. So this is actually something that we can set up as we create our tokenizer. We can say OOV token. And this basically allows us to just assign something that says, hey, if we've never seen a word before, just replace it with whatever we put in here. And so it's not uncommon to just say something like this, where you say angle brackets out of vocabulary, right? And so this is just going to replace, we've never seen a word before. We're going to replace it with that. And that gives your model an ability to sort of squint.
I found this on the web.
Oh my gosh, y'all. I really don't like when my watch talks to me. I need to just turn it off. But the out of vocabulary token, sometimes you'll even add the part of speech. So you'll say out of vocabulary noun or out of vocabulary adjective, which gives your model sort of more to work with. But just picking an out of vocabulary token can be helpful. So we're going to create a tokenizer using that. And now we can actually fit our tokenizer on our text. So the tokenizer will actually run on the data that we're providing it. So we'll say tokenizer fit on texts, and we can pass it all of our training data. So here we can also we can just grab the vocab size here and say vocab size equals len tokenizer word index. So the tokenizer by default builds a word index that just gives a number for every unique word it sees. Excuse me. And we can print our vocab size just for our own edification. And this is cool. It's a lower number, right? What was the first one? 27. Yeah, 27,000 versus 23,000. And so a lot of those words we're missing just because we're only operating on a subset of the data, right? We've only got 80% of the data. But some of those are gone because we removed stop words as well, right? So we have functionally reduced our vocabulary size by quite a bit. So now we can finally create our sequences for training and testing. So we'll say train sequences is equal to tokenizer text to sequences. This is one of the, I have rarely done an NLP project where I have not used text to sequences. This is like maybe my favorite Keras function that I have used ever. So we'll pass in our train data, and then we can do this again for testing data. And we can take a little look at it. Tokenizer has no attribute. Texts. Texts plural. That's how they get you. They make it plural. And test data. Oh, right. It's called validation data. Bleh. Okay, so now we have some good sequences. And just for our own interest, we can just say, well, what does one of these look like? And this is what it looks like right now. So if you go back to this idea of the word index, remember I said it just gives every word a number. And so our sequence is literally just a list of these numbers. And so you could even go in, and I believe the word index, you can put in a number and you can see what word it represents. Oh, no. Is it the, let's see. I think you can put in a word and get the number. Let's see, Keras, tokenizer, word index, get word from index. Oh, interesting. Okay. Apparently it's a little bit of a hassle. You have to get the individual items and reverse them into a dictionary. Well, we don't got time for that. In fact, we're almost to the end of the stream. So I think we're going to finish our pre-processing, and when we come back on our final day, we'll actually get to see some results. Which, of course, you can run ahead and actually run it. But yeah, maybe we'll be doing Keras pre-processing today, and hopefully we can finish actually getting a model. We can get a simple model out there, and then on Thursday, we can build our big model. Oh, also, really big announcement. Not actually that big. We changed the time of the posted time for our stream on Thursday has changed. It used to be like earlier in the day, and I was still working. I was like, hey, Mary, I'll still be working at this time. Can we do it later? And so now it is at, let me actually just not be a liar and pull it up for you. It is on Thursday. It is at 6 p.m. I guess that's 6 p.m. Eastern time. Yeah, everything is in Eastern time. So that'll be 9 p.m. for me. So that'll be a good little late night hacking sesh with Will, and we will do the art tour, and we will get some good data or get some good results from our model. Those are my two promises. Right on. So we have our sequences. Now we want to pad them. So we can first grab the max len of all of them. I'm kind of curious to see how long this is. So let's say lengths is equal to len of I for I in train sequences. And I'm actually kind of curious to see, we can do a histogram here of lengths. This should show us, okay, great. This should show us how long our headlines are. And so you can see that most of them fall in between, like around the kind of 7 to 10, 5 to 10 words per headline. So they're really not that big. They're probably actually quite a bit smaller because we've removed all the punctuation and stop words. Before we did that, they're probably bigger. Oh my goodness. Okay, I pranked myself. So we have not changed the time yet because I'm bad at time zones. Fancy Appleby, thank you for yes, that is exactly correct. So I need to actually I need to ask Mary again to actually change it up there. But yes, we'll be doing it later. Keep an eye on the Discord and on the schedule. But yeah, we'll get it out to you. Also, I had not seen it in front of me, so I'm going to mispronounce it. But it was Embacher or something like that, who won Kahoot yesterday. I did talk to Mary, and I think we're going to be able to get you some swag for winning Kahoot. So so let's keep in touch. But I don't think that person's on stream right now. If they are, say hi. Okay, good stuff. So our average length looks like it's kind of in the 5 to 10 word area. We can just find the maximum. So what if we say max of our lengths? 27. Okay. So 27 is not even that big. And so why don't we won't have to cut off anything. Sometimes if some of them are really long, you'll actually say, hey, we're going to trim all of our sequences down to, sometimes you'll say 50 words. Sometimes you'll say 10 words. You might just make it smaller. But in this scenario, 27 is not that big. So we don't have to trim at all. So what we can say is our training data set padded. We'll call pad sequences. And we'll pass in our training sequences and just set max len equal to, we call this max len. Equal to max len. And we'll say padding post. So this says if we're going to add padding, add it to the end, not the beginning. And we can do just this exact same thing for our validation. Validation padded, validation sequences. That should pad our data for us. And now I think we're in shape to actually build our, to actually build our model. So we'll build a very simple, dumb model, and then we'll call it a night. Let's see. Fancy Appleby and Polar Void. Do I get swag for being second? Do I get swag for being funny? You know, I want to say yes. I think the thing is we have to have some kind of rule. Oh, y'all, okay. If y'all have been submitting here's what we'll do. Folks that submit feedback for all of the sessions, depending on how many there are, we might have to do a raffle. But if there are only if there are only like 4 or 5 of y'all, then maybe we'll send swag to. We'll try to get swag to everybody who has responded to all of them. We might have to do a raffle, so I'm not promising this. We might raffle it off. But yeah, giving me the feedback at the end of every session is super helpful for me. It's weird. I know things about your lives, and I want to be like, I don't know. I feel like there's like great Global Hack Week ML track drama now. So yeah, it's sweet to hear from you in the feedback forums. Okay, so we're gonna do a very basic model, let her rip, and call it a night. So the sort of simple way that we create a model with Keras is with this sequential model. So we can say tf.keras.sequential. And what this gives us is basically we can pass it a list of layers. And inside this list, we can just basically, this is where I said it's kind of like Legos where you smash them together. And we can basically pick whatever layers Keras gives us to kind of Lego together and build something up. And the sort of first thing that I want to do is to make an embedding layer. So we actually talked about this at the very beginning when we talked about semantics and the idea of like what do words mean. And I brought up the word embedding example of king and queen and man and woman. We can refresh your memory. Is it word embeddings, king, queen, man, woman? Okay, yeah. So this was kind of the idea is, oh, no, I don't need that. Oh my gosh. But this idea that you can actually get a set of numbers that represents your word in conceptual space. And so that's what an embedding layer will do. And so the first layer I want to add is an embedding layer. So we can say tf.keras.layers, and then we have the whole world of layers in front of us. So we can say embedding. And the first thing you have to enter is what is the size of your vocabulary coming in. And so we already have our vocab size, but we have to add 1 to it because we added our out of vocabulary token. So if we didn't add 1, it wouldn't have space for our special out of vocabulary token that we added. And then the second thing you add on after that is what is the size or the dimensionality of your embedding. So in our example of the 2-dimensional king, queen, man, woman, that was a 2-dimensional word embedding. But usually, in order to capture more nuance, we actually give our word embedding a rather big dimensionality. Just for the sake of sort of it being speedy, let's start with a dimensionality of 16. This is smaller than you would normally do, but we're going to make it kind of small on purpose. And then we can use our input length and say max len, which we already established to be 27. Awesome. So now what I want to do is, because we want to start with a really simple model, I'm going to do a flatten. So we'll say tf keras layers dot flatten. And because when we enter here, we have a sequence of a bunch of embeddings, and we want to flatten those down to a single one. And so basically, it's going to average all of your word embeddings together. And so this is really not a great way to do this. But again, this is kind of the simplest model we can build is get your embeddings, flatten them, and then do a simple activation at the end. So you will often hear people talk about how you have to have some kind of activation at the end of your network. Oh, did I misspell flatten? Oh yeah, flatten. And we're going to use for this what's called a dense layer. So we'll say .layers.dense. And this basically means everything in the previous layer is connected together to give us this next layer. And we'll say 1 is the number of output units. And in this case, we only want 1 because this is the is it sarcastic output, right? And so this 1 should be, it should light up. This neuron should light up if it's sarcasm, and it should be silent if it is not sarcasm. And we can say activation equals sigmoid. The sigmoid function is one you see a lot in machine learning, but it basically just takes any number. I just want the image. it takes any number of inputs. So your input is on the x-axis here, and anywhere from negative infinity to positive infinity, it will sort of squish those to be in between 0 and 1. So if you have negative infinity way down here, it'll end up being basically 0. And if you have positive infinity, it'll end up being basically 1. And in between there, you tend towards 50-50. So this is a way of kind of giving us a probability of is it sarcastic or not. Sweet. So now that we have our model, we can compile it with a couple extra things. So we can say model.compile. We have to specify the optimizer. So compiling basically just says, hey, get this model ready to actually be run. And we can say the optimizer is Atom. I'm just going to come clean and say, I understand the need for an optimizer. It's the way of it's how you do the math on gradients to determine how you should update in the future. I actually don't know anything about the Atom optimizer, but it's kind of the normal one that everybody uses, and you have to specify it. Honestly, it's surprising to me it's not a default. The default optimizer is RMS prop, which is, I don't know, interesting. Okay, so we also need to specify a loss function. We'll talk a little bit more about the difference between accuracy and loss in probably, I guess, next time. But our loss function will say binary cross entropy. And the very simple way of explaining this is that we care about accuracy, but accuracy is like a really all or nothing kind of metric. And in reality, we actually care if the model was confident or not. Accuracy just cares, well, did you guess yes or no? Whereas loss can actually care about, well, were you confidently wrong, or were you like, I'm not really sure? That's sort of the simple version. But metrics, on the other hand, will just say accuracy, and that will be sort of our final way of measuring. And so after we compile it, we can get what's called a summary, which will just show us kind of what does our model currently look like. So we have our embedding layer, and then we have our flattening layer, and then we have our dense layer here. And something that's interesting to call out is the number of parameters. So when we talk about how big is your model, this is usually what we're talking about, is how many different parameters could change. And this is basically the capacity your model has to learn different things. And so if you have a higher number of parameters, basically your model has a bigger brain. And that has certainly some positives and some negatives to it. Okay, so the final thing we're going to do is we're actually going to try to fit our data. I am going to attempt to use the GPU, which, if I remember correctly, you can say with TF device. This is code that I'm only running because I am currently on Colab, but I will say that if you are using your own fancy hardware, that you should try to figure out how to use that fancy hardware. And if you really want help, you could fire your bug into the chat. We could try to help you out. But no promises. But if you're in Colab, you should be able to select the GPU by saying TF device and device GPU, and then we can do a colon at the end. I'm going to actually see if I think I'd have to restart this if I want to change the runtime. Let's see. Will it make me premium GPU? Sure. Let's just get it all. It might make me. Oh yeah, it did. It killed the runtime. Okay, yeah. I was gonna try to avoid that, but it's whatever. This shouldn't be too hard to just rerun all this. But some of this we really just don't need to run again. But hopefully it's faster because I'm using the fancy hardware. Can you tell I'm like really not a hardware guy? Okay, so we are reconnected and we should be able to use the GPU now. And what we can do is we can say model.fit, and we can pass it our train padded data, and then our labels we'll just turn into an array our training labels. And then we'll also pass it our validation data so it can actually test for us. This is a really nice thing about Keras, is that if you give it validation data, it will actually, at the end of every step, run a validation step for you. Polar Void says, I don't think that's how it works. Wait, remember to turn on your GPU to Colab. Yeah, you got to restart. Yes. If you turn on now, it'll reach the runtime. Okay. Wait, Polar Void says, I don't think that's how it works. Is it still, are you still saying you don't think you have it right? I mean, we'll see. We'll give it a shot. But yeah, let me know. Let me know what I'm doing wrong. Validation data. So we will say test padded NP array. Same thing, just turning our labels into an array. So we can pass in our validation labels, and validation padded. So giving it that validation data, it should sort of tell us how we're doing as it does it for us. And I don't know how long this is going to take. So usually I like to start small. So let's say, so an epoch is basically how many times the model runs through all of your data. And so let's say 5 epochs. And hopefully that won't take too long for us. And yeah, we can turn on the verbosity. I mean, heck, let's say verbose equals 2. I like having lots of information. And then we'll store the history in a variable called history so we can access it later. And let's see what happens. Fancy Appleby doing 250. Oh, wait. Verbose 3, it's not telling me anything. Wait, does verbosity increase as you give it a smaller number? That's confusing. Okay, cool. We're doing quite well. So actually good for us. So if you see here, our accuracy is basically the accuracy we're getting on our training data, on the data that our model is already seeing. Wait, yeah, I'm curious for folks who did not turn on GPU, how fast is it running for you? But so our accuracy here is like basically 100%. It looks like each time we might be getting 1 or 2 of them wrong. And then, but we don't really care about how well we do on data we've already seen. We really care about how we do on data we haven't seen, right? And the data that we haven't seen is our validation accuracy. And that we're getting like 80%, which on the one hand is not 100%. But on the other hand, if we go back to the model we made, what was the best? The best that we did was, yeah, it was like 70%. So using this kind of bigger, even a really, really small version of it, this bigger model, we're already yielding sort of better, more impressive results. And so I think that's a great place to leave it now that we have spent, y'all have spent like 2 hours with me. It has been a trek. It has been a journey. Fancy Appleby got 1 accuracy, but hey, you know what? That's random noise, my friend. But I'm very proud for you. I'm very happy for you. I think it's satisfying in that same way that getting exactly 50% accuracy was satisfying. So thank you so much for tuning in. Next time, we're going to try to beef up our model a little bit. If we have time, I might actually want to talk about explainability and try to figure out like what can we learn from this model. What can this model actually tell us about sarcasm, which I think would be very interesting. But beyond that, yeah, we'll give our feedback form out there. Let me know if we're going too fast or too slow. So far, folks have felt like this has been a pretty evenly paced course, which has been not course. It's not a course. What am I talking about? Workshop, track. We call it a track. And that's great. But if it feels like we're ever getting too fast, if there are specific things that we have not gone over that you want explained, or you have other random questions, drop them in there. And yes, if you give me feedback for every single session, then we'll enter you in a raffle to maybe get some swag. And yes, Fancy Appleby, I feel like y'all have been getting a little bit pushy where you're like, wear the flower crown, play the kalimba. But when you ask and you're polite about it, I'm more than happy to. But hey, it's been great to have you here. It is always a joy to do some machine learning with the Global Hack Week crew. I really appreciate everybody who has stuck with it. And yeah, I am more than happy to play some Kalimba to peace out, y'all. All right, friends. Thank you so much for being here. Watch the Discord to see what time we change it to. It will almost certainly not be the time that we have originally, but cannot wait to see you there. We will do the art tour, and we will finish out our model. So yeah, happy Tuesday and happy hacking, friends. See you next time.